And I want to share my screen first before turn it over to Ali. I just want to show you. Okay. So, I just want to make sure that you guys know that you can actually go into your quizzes and be able to see the exam, not only your grade, but also my comments. So make sure you're able to do that. And you only have a week, 1 week to do so, because it kind of forces me to select number of days that allows you to see the comments, so that you have a 1 week to check the comments. And also I posted here the key for the exam and to compare your answers to the key. When I tell you sometimes see key, sometimes they give you a specific answer because you are being creative in the way you answered the question. So I give you specific comments. Otherwise, if it's standard, I would just say see key. So please do so within this coming week. And also I want to say that, that there is another assignment that I'll create for practice problem set 5. You'll find them under week 11. I did not post any lecture material because it was posted under week 10. So soy protein or legume and oil seeds, our lecture is here. So I didn't post anything under lecture material this week. But then I opened the practice problems and I'll create an assignment for that. And I also opened the key for the 4th assignment. Oh, I didn't open it. Well, I thought I did. Okay, so never mind. Currently not signed in on this computer, but I thought I did. Let me check the other place. But anyway, the assignment will be opened for you guys. I don't know when. I should probably make the due date sometime after spring break, not this. Yeah, so you have time. You don't have to worry about it now. I guess that's it. I have to show you here on the screen. Don't think I missed anything. So I'll stop sharing. And Ali,
we can go. Okay.
Yeah, you guys can start.
Hello,
I think
everyone.
I figured out the spotlight thing here. Okay, you can see that, right? The spotlight.
Mm-hmm.
No?
Yeah.
Can you
I
still
can see
it?
that. No,
okay.
no.
Okay, 1 second. Sorry.
That's okay.
Okay.
Yeah.
Okay, you can go, Moa.
Hello, everyone. Good afternoon. My name is Moat Alisa, and my partner are Kenzie McClintic and Ali Schneider. And today we're going to present the effect of environmental condition on emulsifying properties of whey protein. Next. A brief introduction about whey protein. Whey is a milk protein, represent 20% of the protein. And whey produced from cheese making as byproduct and classified based on protein concentration. If it's between 30 to 85%, we'll consider it whey protein concentrate. If it's above 90%, will be whey protein isolate. And we could produce the whey protein concentrate from byproduct by ultrafiltration. And then from whey protein concentrate, we could microfiltrate it to produce the whey protein isolate. And whey protein has globular, like globular protein with good functional properties. Next. In this structure, The main functional proteins and larger compounds of whey protein are alpha-lactoalbumin and beta-lactoglobulin. And they have very order secondary structure. Can you hear me well?
Yes.
Okay.
Yeah.
Yeah, and they have a very order secondary structure. In beta-lactoglobulin, they mostly have beta sheets, which gives the heat stability, and that denature at 73, while the alpha-lactoalbumin denature at 63. Beta-lactoglobulin has one free sulfhydryl group, and that's very important functional group in gelation mechanism. Next.
Okay, so protein structure changes with environmental conditions or extrinsic factors. These include temperature, pH, salt type and concentration, and protein concentration. Similarly, processing also affects the structure of protein, thus the functionality. For example, temperature significantly affects whey protein denaturation, causing these globular proteins to unfold, exposing hydrophobic groups, which can be beneficial to some food applications like emulsions. This makes the protein more balanced with hydrophobic and hydrophilic regions, for example. So because we're focusing on emulsification of whey proteins exposed to different environmental conditions, this is just a quick review of emulsions. So this means that there's two immiscible liquids like oil and water, where one phase is dispersed within another phase as droplets. This figure shows an oil and water emulsion with proteins acting as an emulsifier. So the protein moves to the interface and aligns its hydrophobic and hydrophilic groups appropriately, forming a film around the oil droplet, and then this stabilizes the emulsion. So a protein's ability to emulsify depends on a lot of factors like the intrinsic factors, surface hydrophobicity, charge, and flexibility. And then these are all dependent on extrinsic factors like temperature, pH, and processing. So the papers that we're reviewing will focus on how extrinsic factors can be altered to enhance a protein's emulsification activity and stability. So the first article is from LWT Food Science and Tech, and it looks at the effective heat treatment on the structure and functionality in an emulsion of whey protein concentrate and whey protein isolate. These are the justifications. They want to look at the effects of pre-treatments and just get a better understanding of this. This is from 2018. Article 2 is about the effects of pH and temperature pre-treatments on the structure and emulsifying ability from 2015. The justification for this paper involves just that whey protein has economic and nutritional value, and they just need, once again, a better understanding of these pre-treatments. And then Article 3 looks at the impact of ultrasonic power and pH on the structure and emulsifying properties of whey protein isolate from 2019. And this is a pretty new area, so we need to understand better how this could impact whey protein.
So the first article's objective is to investigate the effect of heat treatment on the physicochemical and emulsifying properties of polymerized whey protein isolate and polymerized whey protein concentrate. They acquired their whey protein isolate samples from Bongard's Creameries and their concentrate samples from Fonterra. So the whey protein was made up into solutions at concentrations of 8, 10, and 12. Then the samples were continuously stirred for 30 minutes at room temperature and stored overnight at 4 degrees Celsius to complete hydration. The pH was then adjusted to 7 before the samples were incubated in a water bath for 30 minutes at 80, 85, and 90 degrees Celsius. The samples were then cooled to room temperature and stored at 4 degrees Celsius. Next. The methods that they used for analysis were the total free sulfhydryl groups, which were determined to evaluate the effects of heat treatment and protein concentration on the covalent interactions of the whey proteins. They also looked at fluorescence analysis, which was used to show the degree of whey protein unfolding. SDS page, which I'll mention here, but I'm not going to go over in the results. But they used it to measure the extent of whey protein polymerization. Zeta potential is commonly used in the interpretation of protein suspension stability. The viscosity of the samples was measured to see if the denaturation of the protein increased the viscosity due to more interactions with the water. TEM was also used to measure the microstructures of the samples, but I also won't be talking about this in the results. And lastly, they looked at the emulsification activity and stability of emulsions formed by homogenizing the protein solution with soy oil. Next. Sulfhydryl groups of the native protein molecules are buried in the tertiary structure, and denaturation of protein will make these groups accessible for further reaction. The results here show that heat treatment resulted in a significant reduction in total free sulfhydryl groups of the whey proteins. And this reduction in the polymerized whey protein might be due to oxidation or conversion of sulfhydryl groups into disulfide bonds. No significant difference was shown between 85 and 90 degrees in some of the groups. And this could be because the degree of denaturation gradually increases with increasing temperature. Next. Oh, wait. Okay. So according to these results, the fluorescence increased in higher concentration and higher temperature samples. As stated in the article, this could be because heat treatment resulted in more unfolding of the protein molecule, which exposes more hydrophobic groups from the core of the globular protein and thus leads to an increase in fluorescence intensity. Interestingly, the fluorescence activity was decreased at 90 degrees Celsius, but this might be due to polymerization induced changes in the microenvironment or occlusion of tryptophan residues from the aqueous environment. Next. So in this table, you can see that the zeta potential of the PWPC and PWPI were significantly lower than that of native whey protein dispersions. This is beneficial for stability because if the charge is more ionic, then the protein will interact more with water. They concluded that different temperatures and concentrations seem to greatly impact the zeta potential. And this is obvious when you look at the significant decrease in zeta potential at 85 degrees Celsius in both the PWPC and PWPI at the 8 and 10% concentration levels. As you can see here, the viscosity increased with increase in protein concentration and temperature. And they stated in the paper that this may be due to the denaturation of the globular protein because the alteration in protein conformation increased the surface area and exposed buried peptides and amino acid side chains, allowing them to interact with water, which increases the viscosity. The emulsification activity and stability were measured through EAI and ESI, and this shows that the EAI of unheated whey protein samples was significantly higher than that of the polymerized whey protein samples. And this is because the whey proteins experience loss of emulsifying abilities with thermal processing. And in table 4, the ESI of the native whey protein isolate and polymerized whey protein isolate was significantly higher than that of the native WPC and PWPC under the same conditions. According to the authors, the reason behind this was that the whey protein isolate can produce a larger electrostatic repulsion than the whey protein concentrate during the unheated or heated conditions, which is conducive to stabilizing the emulsions. Furthermore, just one more point. Furthermore, the EAI and the ESI of the polymerized whey protein isolate were significantly higher than that of the concentrate, the polymerized concentrate. And the ESI of the polymerized whey protein samples were higher than that of the native protein samples because of a denser network. Okay. The conclusions that they drew from this study were that heating induces the formation of large protein aggregates, increasing the temperature and concentration increases viscosity. The content of the free sulfhydryl groups, Zeta Potential, and EAI of the polymerized whey proteins were lower than those of native proteins under the same conditions. And whey protein isolate has better emulsification abilities and is more stable and homogeneous than whey protein concentrate. Some critiques and recommendations of mine were that the protein I noticed was from different suppliers, which could lead to varying results. So maybe it would be better if they had the concentrate and the isolate come from the same supplier. Some of the results in the discussion were not very thorough in the paper, so I would also recommend that they give more thorough explanations of the tables and figures. Also, the microstructure methods, like the TEM and STS page, seemed kind of like an afterthought in the paper, and they didn't really discuss much about their findings and the results. And I also wondered if viscosity was a necessary measurement for the study. And another recommendation would be that maybe they use a more direct method to measure particle size.
Okay, so Article 2 looks at the effects of pH and temperature pretreatments on whey protein isolate structure and its emulsification ability and stability. So whey protein isolate was provided from Davidson Foods and used to make 0.1% whey protein isolate solutions in water, adjusted to 3 different pHs, so pH 3, 5, and 7. One thing I want to note is that they said that the water was adjusted to the pH, and it wasn't very clear whether or not the protein solutions were. So then this was stirred at room temp for an hour, then incubated in a water bath at 3 different temperatures, 25 degrees, 55, and 85 degrees C, and then cooled to room temp. These treated protein solutions were then tested for their structural properties. So with this protein solution, the secondary structure was evaluated by CD, surface hydrophobicity with a fluorometric assay with the probe, and then intrinsic fluorescence, looking at aromatic amino acids with the SPEC method, surface charge and aggregate size by Zeta sizer, and then the protein solution with oil was evaluated for its emulsification stability and activity, as well as interfacial tension. But for the sake of time, I'm not discussing the interfacial tension here because there wasn't a significant effect of temperature and only slight differences by pH. So looking at protein secondary structure, flattening is assumed as a loss of secondary structure. So one thing I want to note first is that this chart had no key, or this figure had no key in the description or on the figure itself. So I'm relying on their discussion to identify which line is with which temperature. So this is obviously a big error on their end. But anyways, based on the discussion, we can see that at pH 7, that's A, there was little effective temperature treatment. At pH 5, which is B, that there's loss of secondary structure with the 85 degree C treatment. And this is near the isoelectric point of whey protein. So it's assumed that this was caused by disruption of hydrogen bonds at this higher temperature, causing unfolding. So because the protein's nearly at a neutral charge at this point. And then in overall, the surface charge at pH 3 and 7 help prevent changes in tertiary structure, resisting denaturation, allowing for refolding of proteins when brought back to room temperature after heating, whereas this 85 degrees C treatment left the protein nearly totally denatured. Next, they looked at hydrophobicity, both intrinsic fluorescence and surface hydrophobicity. So intrinsic fluorescence measures the fluorescence of aromatic amino acids. There are similar trends for the 25 and 55 degrees C treatments, but the fluorescence intensity at pH 5 of the 85 degrees C treatment shows that, that there's an increase in fluorescence intensity, which is due to the unfolding of the protein, exposing hydrophobic groups near the isoelectric point. One thing to note is that there was no discussion of intrinsic fluorescence in the paper, and it follows a similar trend to surface hydrophobicity, so this method seems a little bit unnecessary. So similar trends are seen for surface hydrophobicity, with 25 and 55 degree C treatments having similar trends. The highest surface hydrophobicity is with the 85 degree treatment at pH 5, and that's likely due to the low net charge near the isoelectric point, then unfolding of the tertiary structure, exposing hydrophobic groups, which then interact with the probe. And then on the other hand, the reduced fluorescence or reduced surface hydrophobicity can be attributed to the greater surface charge at pH 3 and 7. So looking at surface charge, we can see the expected trends basically. So there's a net zero, nearly net zero charge near the isoelectric point at 5. This paper lists the isoelectric point of whey protein as 5.1 to 5.4. And then there's the positive charge at pH 3, negative charge at pH 7, and the charge as expected changes based on pH, which relates to the protonation state. And in this graph, we see that there's little effective temperature on charge. The charge of the protein relates to the electrostatic attractive and repulsive forces, which can lead to high solubility or protein-protein interaction and aggregation. So looking at aggregation, we can see that at pH 5, due to a reduced electrostatic repulsion, there's more aggregation via hydrophobic and other non-covalent bonding of the alpha-lactalbumin and beta-lactoglobulin. Interestingly, though, we see that there's smaller aggregates with the 85 C degree treatment at pH 5. Their theory is that the high temps led to formation of aggregates along with denaturation. So there's basically just smaller aggregates at this temperature treatment. Next, these emulsions that we're looking at were formed by homogenizing the protein solution with canola oil. So the emulsification activity index gives us an indication of the surface area stabilized by the proteins. And we see that this declines at pH 5, then increases again at pH 7. And this was correlated with aggregate size because larger aggregates need more time to migrate to the oil and water interface. This results in the lower emulsification activity. And then at pH 7 and 3, the proteins had faster migration to the interface, and so a higher emulsification activity. So for stability, we see a decline at pH 5 and then increase at pH 7. Emulsification stability is associated with the electrostatic repulsion between droplets, which explains why it was lower at pH 5, close to the isoelectric point, and conversely higher at pH 7. The effective temperature was also greatest at pH 7. You can see that it differs more at this point. The stability of the 85 C degree treated sample was attributed to the higher surface hydrophobicity promoting flocculation of the droplets. This is what the authors stated, although the differences in surface hydrophobicity at this pH were very minimal, so I don't know that this is the best explanation. And then correlations, there were correlations made with emulsification stability. And I think it's kind of strange here. I put it in orange that the R was pretty low and that they changed the p-value with whatever they were correlating this with, so surface hydrophobicity, charge, or size. So I don't really think that those are great correlations to make. So overall, their conclusions were that pH and temperature treatments can alter the structure of whey protein isolate, that reduced aggregate size seems to improve emulsification activity, and that surface charge and surface hydrophobicity impact emulsifying properties, but there didn't seem to be very clear trends, and that proteins are most stable away from the isoelectric point. And then some critiques, some of the methods were kind of questionable and hard to understand. So the whey protein isolate solutions were listed as 0.1 grams per 100 grams protein. And I think they meant to say 0.1 grams protein per 100 grams water. Also, I'm not sure if the water was pH adjusted or the protein solution. The data wasn't always clear. They didn't even have a key for one of the figures. I think the figures also could have been listed in a table with like significant differences listed as well. Sorry, and then the discussion wasn't very thorough or clear. Yeah, I think the data could have been explained better and explained by like the EA by surface hydrophobicity in other tests that they ran. And then the correlations seemed inconsistent overall. Up to you, Moaf.
In Article 3, the objective investigate the influences of pH values and ultrasound on the structure, aggregation, dissociation, and emulsifying properties of whey protein isolate molecules. Next. For the materials and preparation, the whey protein isolate started from they brought it from Mullins with 93.5% protein, and they made 5% whey protein isolate in deionized water. Then they stir for 2 hours, and when it's completely dissolved, they stir it. They keep it at 4 Celsius temperature for 12 hours, and then they adjusted the pH with 3, 5, 7, 9, and 11. After that, they treat the samples with ultrasonic treatment for 30 minutes with 120, 360, and 600 watt. And finally, they freeze drying the sample and store them at -20 Celsius until they analyze the samples. Next. Here is the method of analysis, and I won't cover the intrinsic fluorescence for the sake of time, and this is what they measure: the particle size, surface hydrophobicity, and free sulfhydryl and protein secondary structure by FTIR, and surface properties by using scanning, electron microscopy, and emulsification, stability, and activity. Next. For the particle size distribution, here we see in general that the particle size of ultrasound treatment whey protein isolate gradually decrease as the ultrasonic power increase from 120 to 600. This was likely due to cavitation effects, which create instability and high shear forces, resulting in a more uniform particle size distribution. Next. For the surface hydrophobicity in the left chart, compared with untreated whey protein isolate, the surface hydrophobicity of ultrasound-treated whey protein isolate were higher and increased significantly with increasing ultrasound power. In the right chart, the sulfhydryl, the free sulfhydryl in pH 5 and pH 7, whey protein isolate increased as the ultrasonic power increased from 0 to 600. The sulfhydryl group of whey protein exposed at pH 11 due to strong alkaline condition that completely broke the disulfide bonds of whey protein isolate, resulting in severely damaged protein structures. Next. For the emulsion activity and stability, in the left chart, the emulsion activity, in pH 7 and 9, whey protein isolate gradually increase as the ultrasonic power increase from 120 to 600, compared with those of untreated whey protein isolate. At pH 11, whey protein isolate under the same ultrasound treatment, the reduction and in emulsion activity of whey protein isolate decreased likely due to the decreased number of sulfhydryl groups. And in emulsion stability in the right side, the emulsion stability in pH 3, 5, 7, and 9 significantly increased with increasing ultrasonic power from 0 to 600. Next. For the protein secondary structure, the alpha helix or the level of alpha helixes of whey protein isolate at all pH values significantly decrease at 600 compared with untreated whey protein isolate at all pH values. This indicates that ultrasound broke the hydrogen bond of protein moleculars and destroying rigid protein structure and improving protein molecular flexibility. Next. In scanning electron microscopy, the ultrasound treated whey protein isolate B, D, F, and H, which is indicated in the red circle, showed more sheet structures compared with untreated whey protein, which is next to the red circle. And the down right corner, sample J, was broken into much smaller sheet-like structures, indicating that the whey protein isolate structure was severely disrupted in extremely alkaline conditions under high-intensity ultrasounds. This shows that ultrasonic treatment could produce more irregular sheets-like structures. Next. To summarize the results, the ultrasounds combined with pH treatment narrowed the particle size disruption of whey protein isolate and also enhanced the surface or average surface hydrophobicity and increased the sulfhydryl level and improved emulsion properties. In critique and recommendation, the method and results are disorganized. In the method, they combine some together and have them in certain like organized, and then in the results, they just mess them up and you have to find them. It's not the same order. There are no enough explanation for the results before concluding. They're most likely describing the results instead of discussing. And there are errors in statistical analysis for significant. They use ANOVA for all samples instead of dividing by pH. And in the FTIR and SEAM analysis, they have only one sample of ultrasound treatment, 600, and they never mention why they doesn't do the 120 and 360. Next.
Overall conclusions from our 3 papers were that whey protein structure can be altered with environmental conditions and pretreatments to make it more suitable for different applications. Some results seem to contradict one another, so a temperature at 85 degrees may or may not improve emulsification. The suitability of whey proteins for different applications are very dependent on protein concentration, pH, and temperature. Furthermore, ultrasonic treatment seems to improve emulsification ability, but the impact of pH needs more investigation and the method needs more development. Some overall recommendations and critiques for our combined papers were that The analysis of the formed emulsions rather than the protein solutions might be more useful. The methods and discussion of results should be more thorough, and the ability to tie the objective to a clear conclusion is vital. And lastly, consider the journal before reading, because you have to be more critical of the methods and conclusions for lower quality journals. Thank you.
Okay, good, right on time. So thank you all, three of you. So we'll open it up for questions. Either type your questions so that they can read it out, or you can unmute yourself. I have a few questions, but I will wait until we get questions from students.
Yes, I think it was Kenzie, the first article. You mentioned errors in this statistical analysis. I guess I may have missed it. What were those errors?
Whoops, didn't realize I was muted. So in one of the tables, hold on one second, let me pull it up.
Do you want me to present again, Kenzie?
Sure. So on the total free sulfhydryl group slide, they said in the results that the content of the free sulfhydryl groups of the polymerized whey protein concentrate at 80 degrees Celsius is significantly higher in comparison to 85 and 90 degrees. And if you look at that table, the superscripts show that there isn't a significant difference. So I noticed that that was a statistical error.
Okay, other questions, please?
I have a question, comment dash question. I don't know what it is exactly. So on the third article, when they use ultrasound, does it mention if they control the temperature during the process? Does it, sorry, I didn't see the methodology. Because,
they never mention about it during the process, but they say after the ultrasound treatment, they control it in 25, but they never mention if it's during the processing or after. It wasn't clear.
Yeah, like my point is this, because usually we use ultrasound not for protein modification, but like to make emulsions, right? So you decrease the size of the droplets, really awesome, but it's a lot of energy, like 600 watts for 30 minutes. That's a lot of power being put on this emulsion.
Yeah.
So it's difficult to know how much of this changes may be actually for energy being transferred to the bonds of the proteins, but also for the temperature increase. Usually we used to use like 5 to 3 minutes, and that would be a significant increase of temperature. So if they leave it for 30 minutes at this high amount of energy, like you may have actually changes due to temperature increase and not necessarily to the cavitation of the droplets, right? I don't know, just like something that may interfere.
Just mention something. They use like 2 seconds working and 4 seconds stopping. They don't run it all the time in 30 minutes. And they wasn't clear about it, whether they control the temperature or not.
Maybe the stop moving and stopping, they were hoping to achieve that, but they probably did not explain it. Yeah, there is a question from Chrissy for Kenzie. You mentioned that you weren't sure how necessary the viscosity analysis were, but did they discuss why the viscosity was for the isolate was higher than the concentrate?
So I believe what they said in the article is that this could be because the viscosity of the soluble whey protein aggregates depend on heat treatment as well as on the nature and composition of the whey protein isolate or the whey protein concentrate in the suspension. So that's why the viscosity of the whey protein, or the polymerized whey protein isolate was higher than that of the polymerized concentrate under the same conditions.
So following up on the viscosity, I actually had a question just to relate to what we mentioned in class. How do you think viscosity relates to emulsification stability?
So a more viscous protein solution should be more stable.
Yeah, was
As
that
involved.
was that reflected in their viscosity measurements, Kenzie? Did they see higher viscosity in the samples that were more polymerized? And
Yeah.
therefore, yeah.
Mhm.
So that could explain that's probably where you can bring in viscosity, but if they didn't discuss it, it would have been a good point to discuss that. So the other question I had for that particular paper, why do you think WPC versus WPI, there were differences in the stability? I think the WPI behaved much better than WPC. Did they, okay, let me ask you this differently. Did they prepare their samples based on protein content or on powder base?
I think based on protein content. I guess could it be because, okay, so he's asking why the zeta potential would increase with some heat and concentration increase, but then decrease. Okay, because at like 85 degrees, it looks like the zeta potential decreases and then it increases again at 90. And so they don't discuss this in the paper, but I think it could be because as the protein polymerizes at the higher temperature, the sulfhydryl groups are kind of eaten up and the zeta potential will increase. So the negative charge decreases.
So Kenzie, you didn't answer my question though before you moved on to Devin's.
Oh, sorry, what did you ask?
I was asking why they saw higher stability for WPI compared to WPC, and I asked you if that difference could be to the protein concentration, and it wasn't clear what you answered.
I want to just add something in that paper. They didn't specify how they made the solutions. They just said that these solutions were made. So there's no indication of whether that was on protein content or amount of powder.
Yeah. So if they measured based on powder, then of course in the isolate you have more protein. So that will give more impact to viscosity as well as stability. So that is something that we need to always think about. Is it on protein basis? Is it on powder basis? Because it makes a lot of difference. Okay, so what other? There's Grace and Radhika. They have questions.
Nigel as well.
And Nigel.
I have a question also.
Okay, let's go with from Nigel onward.
Okay, so for Nigel's question, is it usual to conduct pretreatments at 0.1% concentration? That's small. I guess I'm not sure what's normal. All of these papers did things very differently. But I think 0.1 is not very, you can't apply that to real life situation very well. So they probably should have done a higher concentration just to make it more applications focused.
Yes. Yeah, it's very unreasonable, this low concentration. And also at different concentration, you get different effects. of pH and temperature. So, okay, so then Kenzie kind of answered Devin's question, and then Radhika, for you, Ali, again.
Okay, so adjusting the pH of the water instead of the protein solution, that means that, so if they didn't adjust the pH of the protein solution, it's not necessarily going to be at the pH that the water's at, because the protein will buffer a little bit. So I think that the way that they're reporting the results at pH 3, 5, or 7 isn't necessarily accurate if it's not of the protein solution.
Yeah.
So
yeah, of course, the buffering effect of the protein is going to throw off the pH, definitely. Yeah. Okay, so Ali, another question from Grace to you.
So they said for previous results, they said what you have your 0.001, and then for the correlation with the aggregate size, they used that p-value. But then when they stated correlations with like surface hydrophobicity and charge, I believe, they did it at 0.05. So they totally changed it, and it was, yeah, inconsistent.
Wow, 0.001, I missed that. This is, I mean, 99% confidence is 0.01. What is this? This is 99.9% confidence. I don't think anybody.
Yeah, that's true.
Yeah. Okay. All right. So this is a question for moi, Holly, from Holly. So can you comment on the industrial feasibility of ultrasonication? Is it being used? And if so, for what products?
The paper, they say that this is first time they use like pH with ultrasound. So there's been like some studies about single ultrasonic treatment in food proteins, but I don't know about the food industry if they use it or like if it's just in the beginning. No idea.
I don't get the impression that this is being used in the food industry at all. This is like preliminary research. Yeah, Sonny,
yeah, like
know.
I have like there are some studies on it trying to make it more feasible. There are studies, for example, that they use ultrasound to improve when you using pectinase on apple juice, for example, so it helps break the fibers. For example, you doing ethanol of second generation helps break the fibers to improve fermentations during like a beer or like a spirits, this kind of things. So the problem is it's a little bit expensive to run because it requires a lot of energy, but there are some studies trying to apply and emulsification to decrease the droplet size on margarines and these kind of things. But yeah, it's still on the beginning. There's a lot of room for improvement on ultrasound usage for sure.
Okay, we'll take one more question from Samira. I guess she said she has a question, and then I have a question, and then we'll end. Go ahead, Samira.
Okay. I don't know if it was a typo mistake or by the author or not, but Kenzie, for the first article, it was written that the WPI sample from Fontra was WPC and it had more than 90% protein. I believe Fontra produced WPI, not WPC. Can you double check it?
Oh, yeah.
The article?
Yeah.
Because you.
Yeah, I'll double check in the article. That might have been a typo.
Yeah, potentially a typo. This is actually, I have one more question.
Yeah.
I guess, I think two articles, maybe the first one and the second one looked at EAI and ESI, and the impact of polymerization was opposite. And I think Kenzie made that in the conclusion that we got opposite kind of impact. So how from what you learned in class, why would polymerization reduce EAI but yet enhance ES?
So I can start with this one, but
Yeah.
polymerization may reduce the emulsification activity because the larger aggregates take more time to move to the interface.
Yes.
But they might also increase viscosity, which could help stabilize the emulsion.
Exactly. So there's no perfect like synergy. You might want to find kind of a midpoint where you get some of this and some of that. But yes, so it's kind of like, okay, you're enhancing the polymerization, you're increasing viscosity, you enhance stability, but again, the movement to the interface is kind of slowed down. But once they get to the interface and once they emulsify, they form thick films and potentially higher stability. So that's why you see a decrease in one functionality and enhancement in another. Okay, just wanted to make that link for the sake of everybody in the class. All right, this is great. We spent a little bit more time today because it's 30 minutes, so don't charge them for 30 minutes. In terms of when you are filling the time adherence, they adhere to time because they're 3 presenters, and we took a little bit more time for questions. So what we'll do is we'll take a break, about 7 minutes break. We'll come back at 3:55 and I'll have a 55 minutes lecture. Okay.
Oh, I almost forgot my mask. Thanks.
Yeah.
All right, let's come back. I think this was a little bit more than the time we said. I was responding to a few emails. Anyway, so let's get back to it. Is everybody almost back? Waiting on Paul and Nigel. We all here? Yes, okay, good. So I'll share my screen and we'll start with the lecture on legumes and oilseed proteins. Okay. See how much we can cover. Just a reminder, folks, that after spring break on the 14th, we won't have a live lecture, but I will record the lecture next week, so you'll have it available. Please make sure to listen to it before lecture on the 21st, where we come back and we have one group presenting, Brigida and Rediga, on the 21st of April, and we'll continue with the lecture after that, like usual. All right, so some of you might know this, some of you have no clue, which is okay. We'll talk a lot about it today, but let's see if anybody wants to answer this question. So of the following, glycine and beta-conglycine are the main storage proteins in soy. The ratio of glycine to beta-conglycine influence functionality of soy protein, and glycine is the main allergen in soy protein, while beta-conglycine is not. So what do we have here? You can type, you can answer. At least A and B. Yes, so it is D for some of you that are answering. It's correct. Actually, research have shown, multiple research from our lab and other labs have shown that both glycine and beta-conglycine can elicit immunoreactivity in different individuals. So some individuals are reactive to glycine, some are to beta-conglycine, some are to both. So they are both allergens. The both categories are allergens. And yes, we'll talk a lot about them being storage proteins and how their ratio impact functionality and so on. Okay. Now, you'll see a lot of times in papers, if you read papers on proteins and legume proteins, you'll see that they refer to 11S and 7S fractions. And the 11S is the legumin fraction of the legume protein, and 7S is the viscillin fraction of the legume protein. So have you thought about, if you've seen it before, do you know if glycine, well, legumin, let me call glycine legumin, has higher molecular weight? If you have 11S versus 7S, would that mean that the fraction of the molecule or the polymer has higher molecular weight? Does it mean when you have a 7S, which is viscillin, also beta-conglycine in soy specifically, does it mean that it has lower sedimentation coefficient, or glycine has higher sedimentation coefficient? And what is sedimentation coefficient? Maybe we can start with, what do we mean by S, the unit S, or sedimentation coefficient? Any idea?
The time taken by a molecule to I want to say run down a gel, it somehow relates to velocity. And the larger the molecule, the more time it will take to come. So 11S would mean a bigger molecule that takes more time to come. I'm not sure.
Okay, you're heading in the right direction, Radhika. It's Radhika, right? I can't see you.
Yeah.
So yes, you're heading in the right direction, but it's not the time. It's actually the velocity of sedimentation, the rate of sedimentation at a particular gravitational force. So when you apply a specific gravitational force, I think I have the definition here. Yeah, when you apply a certain gravitational force, if the molecule is large, the speed that it would fall and precipitate would be higher. So it precipitates at higher speed than a smaller molecule or polymer. So 11s is meaning that the legumin is of a bigger polymer, so it would fall down at a larger speed at a particular gravitational force.
I have a question on that. Sorry, it's just something that I was talking with Samira about, trying to understand. Like, but when you say large, we're talking about volume density, like a large in volume, large in weight. What's large?
In weight.
Okay.
Yeah.
Thank you.
In molecular weight, and the molecular weight is related to that, to the weight, basically. Yeah. So heavier in weight, not in volume. Okay. Yes. So the answer to the question is glycine, which is a legumin, has a higher molecular weight. It has a higher sedimentation coefficient, and beta-conglycine, which is viscolin, it has a lower sedimentation coefficient and a lower molecular weight. Okay. So legumes and oil seeds. So sometimes we have legumes that are also oil seeds. So for example, soybeans and peanuts. So they are legumes, they exist in a pod. And they are oil seeds because they have oil, high content of oil and high content of protein and close to 0% starch. They're mostly fiber. So they're not starchy. Legumes, non-oil seed legumes, they're usually starchy and they have low fat content. And examples are your peas, chickpeas, beans, lentils, so on. These are the starchy legumes, non-oil seed. And then you have the oil seeds that are not legumes, such as sunflower, rapeseed, which are canola, the genetic modified version of rapeseed, cottonseed, coconut, and others, such as some of those that we work on in the lab, like hemp, camelina, pennycress. Okay. So this is just a brief, again, differentiation when I say starchy versus oil seeds. So the pulses, they have high percentage of carbohydrate, mostly starch and fiber, and appreciable amount of protein, between 20-25% protein, very low lipid, very low amount of fat. But chickpea, for example, you see has more fat content than the other pulses or legumes. If we look at the oilseed legumes, so soybean, it has much higher oil content or lipid content and much higher protein, and carbohydrate are mostly fiber, dietary fiber, and small sugars and oligosaccharides. So you have less than 1% starch material. So this is just to give you a differentiation between starchy legumes and oilseed legumes.
Pam, are all legumes pulses or all oil seeds pulses, or how would you classify?
No. Pulses mostly are your starchy legumes. They're called pulses. Oilseed, soybean is not a pulse. It's a legume, but it's not a pulse.
Got it.
No, it doesn't have, the difference is high in oil, low in, doesn't have starch, almost less than 1% starch. The others are high in starch, appreciable amount of protein, very little fat, and fiber. Okay. Yeah. So moving on, I was looking at the chat. All right. So the proteins in plant sources in general, you have two categories, whether they are legumes or oil seeds. You have the globulins and you have the albumins. So the albumin, really, if we want to think about food functionality, they don't have much of a functionality. They don't contribute to the functionality in food systems. They are mostly a heterogeneous group of proteins that might be enzymes, might be enzyme inhibitors, and might be structural protein to the actual structure of the plant itself. So they are not necessarily, they don't necessarily contribute much to the actual functionality of the protein. Well, albumins are soluble in water, potentially, like we know from the Osborne fractionation. Albumins are soluble in water, and globulins are soluble in salt water. So globulins in plant proteins are storage proteins that the crop, the grain or the seed store their energy source. So storage proteins, and like I said, they mostly in legumes and oilseed legumes. They are referred to as legumin and viscilin fractions mostly. They're mostly legumin and viscilin. And within the legumin and viscilin fraction, there are multiple different types of these proteins. So, and they are 11S and 7S fraction because of their sedimentation coefficient based on their molecular weight, the size, molecular weight and size of that molecule or polymer. So in soy, legumin is known as glycinin and viscilin is known as beta-conglycinin. So in pea, however, legumin is legumin and viscilin is viscilin, and you have conviscilin too. Same with a chickpea, for example. So these are, but in soy, they're mostly known as glycinin and beta-conglycinin. And these are the ones that contribute to functional properties. So the fractions, when we isolate fractions based on sedimentation coefficient, we have the 2S that are usually low molecular weight proteins, or a fragment that dissociated from a larger molecular weight polymer, which can form when we, at particular salt ionic strength or pH, then the larger polymers might break down to smaller subunits, and then they would be in the 2S fraction if we're separating based on sedimentation coefficient. 7S is medium molecular weight, 11S is the high molecular weight. Also, we can form larger polymers, 15S, under certain conditions where we get, more aggregate formed under certain salt concentration or pH concentration. So the ratio is very important in terms of functionality. So the 11S is known to have better gelation characteristics because of the fact that it has more disulfide linkages. So it has sulfur-containing amino acids, cysteine, whereas 7S almost lacks cysteine groups, so they would form very soft gels based on mostly hydrophobic interactions rather than disulfide linkages if they were an isolated fraction. Obviously, a combination would be good. A balance between the two fractions would potentially give you good functionality. 7S, due to surface properties, tend to be better emulsifier, or at least might maybe have better emulsification activity. But presence of 11S contribute to viscosity, thickness of the film around the around the oil droplet or water droplet if it is water in oil emulsion. So the ratio of these globulin proteins is impacted by the variety as well as growing conditions too. So there are soybeans that vary in this ratio from 0.5 to 1.7, whereas in beans you have less 11S to 7S, so the ratio becomes even lower.
I have a question. I feel like this might be kind of a, well, dumb question, but when it's talking like 11S and 7S, that's actually referring to the sedimentation coefficient, right? Or is that referring to something else?
Yes, it is the sedimentation coefficient, which is, it's very common nomenclature in the globulin world of legumes or plant proteins because of their, that correlates to the molecular weight.
Thank you.
Yeah, so the correlation to the molecular weight is here on this slide. It kind of gives you that the protein that has 11 sedimentation coefficient would be high molecular weight versus 2S, for example, would be a low molecular weight protein.
Okay.
Okay, so if we look at legumin, like we said, the sedimentation coefficient really ranges, but the average is around 11S. So it's commonly referred to as the 11S protein fraction. And molecular weight also ranges. So it forms it's a large polymer of multiple protein subunits. And the different subunits in different varieties or variants, genetic variants will have different molecular weights. So you have a wide kind of range of molecular weight of that polymer. And also it differs not only between varieties within one species, it differs between species. So the legumin in soy versus pea versus chickpea, they vary in their range of molecular weight. Question? Okay, so they usually are high in acidic amino acids. So the charged amino acids are acidic, and also the basic amino acid that they are high in is arginine. And the acidic amino acids are glutamic acid and aspartic acid. They are low sulfur containing, so they are low in methionine. So in general, some legumes, well, soy has better content of methionine, for example, than pea. So that's the limiting amino acid, basically, is methionine, which is a sulfur-containing amino acid. Okay, and then legumin is rarely glycosylated. So if it is glycosylated, it's less than 1%, and not all legumin in all different types of beans are glycosylated, but some are. For example, lupin, it is partially or a little bit glycosylated.
I had two questions. So you mentioned that legumin between species differ in molecular weight. They would also differ in the sequence of amino acids, right? And
absolutely. There is a lot of homology, but homology meaning similar amino acid composition and sometimes sequence, but there are some differences too.
Mm-hmm. And we use alkaline extraction for legume proteins because of the high charge amino acids.
Yeah, well, yes, but the pH is not really very high for legumes and pulses. So you can extract them at 7.5, 8.5. So they are more soluble at higher alkaline due to the ionization of OH groups and sulfur-containing sulfhydryl groups. But they are still soluble at pH 7, 7.5. So in our lab, for example, we extract soy protein isolate pH 7.5, which is reasonably not close to neutral.
Pam, your sound is a little bit robotic for me.
Oh,
And me too, yeah. I thought it was my internet, but
Okay. I will assign one of you, I think Ali is co-host, so I'll leave and come back. Which means there will be 2 recordings for this lecture again. I don't know if